Okay guys, so today we would like to evaluate this infinite alternating sum of reciprocals of consecutive odd numbers. So 1 minus a third plus a fifth minus a seventh and so on and so forth up until infinity. So how are we supposed to evaluate this guy? Well, I would like to use a neat trick there. Well, this trick will seem like it just comes out of the blue, but I think nobody really cares about it. Yeah, so let me guys just show it to you. So, well, how can we rewrite this guy out? Well, first of all, how can we write this one in the most inconvenient and the most unintuitive way possible? Well, surely as the integral between 0 and 1 of 1 dx. Well, lovely. Well, how can we, in this same kind of a manner, rewrite this 1 over 3 we've got right there? Well, 1 over 3 will be equal to the integral, that's an awful looking integral, the integral from 0 to 1 of x squared dx. Well, this is true, this is just gonna be x to the power of 3 all over 3 in the bounds of 0 and 1, so a third minus a 0. Lovely. Well, how can we write this 1 over fifth in the, well, least intuitive way possible? Well, as an integral between 0 and 1 of x to the power of 4 dx, and in the same way we can write this 1 over 7 as the integral between 0, that's an awful looking integral, the integral between 0 and 1 of x to the power of 6 dx. But you might ask, how the hell is this mess going to help us? And you will see how in just a few seconds. So, well, if I were now to write a kind of a different sum to the one we have to evaluate right here, which is 1 plus 1 over 3, and then plus 1 over 5, and then plus 1 over 7, and so on up until infinity, I could write it as the integral between 0 and 1 of just the dx, plus the integral between 0 and 1 of x squared dx, plus the integral of the integral between 0 and 1 of x to the power of 4 dx, and then lastly the integral between 0 and 1 of x to the power of 6 dx, and so on and so forth up until infinity. Well, and now if I just wanted to make this guy be the alternating sum we originally wanted to solve, we originally wanted to evaluate, I'll just have to flip those signs out, so I would have to just nicely go on and change those signs here. But now the nice thing is that I can combine integrals together if I'm adding them or subtracting them. Well, if I have an integral of the function f of x with respect to x, and I'm trying to add an integral of a function g of x with respect to x as well, well, I can combine it and say it's going to be the integral of f of x plus g of x, and that's all going to be taken with respect to the variable x. I mean, provided that the bounds of integration there are the same, and well, this condition is surely satisfied in my case. So let me just go on and combine all those integrals together. So I'm gonna get is, well, pretty much just the huge integral between 0 and 1 of 1 minus x squared plus x to the power of 4 minus x to the power of 6, and so on and so forth. I'm gonna take all of that stuff with respect to x. I'm gonna multiply by the dx. But now, well, how can I write this infinite mess, to be honest? Well, this thing right there is just the geometric series. I mean, just think about it. You see, we know the formula for the sum of a geometric series. We know that this looks like 1 plus r squared plus r cubed all the way up to infinity will be equal to 1 over 1 minus an r. We even proved it on the channel using induction. I really hope we did it a few a few months ago, I think. Yeah, and now we can use this formula there in order to calculate what we've got right here, because this is pretty much the same sum, but we've just we've replaced with negative x squared, because I could just go on and rewrite this entire integral as integral between 0 and 1 of 1 minus, and let's say 1 plus, and then negative x squared to the power of a 1, x squared to the power of 1, and then plus negative x squared to the power of 2, and then plus negative x squared to the power of 3, and so on and so forth up until infinity. And so I can just say that this entire integral by this formula right here will be equal to the integral from 0 to 1 of 1 minus x squared, which is 1 plus x squared with respect to x, but you should recognize this thing. This is just the arctangent of x, or Americans would like to call it this tangent, inverse tangent of x, or whatever. So it's gonna be the arctangent of x in the bounds of 0 and 1, but, well, arctangent of 0 is just 0, so this is gonna be pi over 4. And so what we actually end up with is that, well, just think about it, this sum we're supposed to evaluate is equal to this infinite sum of those integrals, which is actually equal to this integral of this infinite series, this infinite power series, which just nicely, very nicely, gets rewritten as this guy over here. And there's one more pretty important caveat, because r here should be in between 0 and 1. Yeah, so in between 0 and 1, and it sure is. We are taking the integral between 0 and 1, and you know, the only slight caveat is that we are actually having the upper bound being equal to 1, but this difference is just, you know, it's just so abysmal that we can not really care about it. And what we actually end up with is, once again, that the sum of 1 minus a third plus a fifth minus a seventh, and so on and so forth up until infinity is equal to pi all over 4. Hope you guys enjoyed it, and see you in the next one.